Okay, today we're going to talk about how we can simplify a square root radical. And so our vocabulary words today are radical and radicand. So a radical the radical that we're going to deal with today is a square root radical. In general, a radical is this symbol right here. Now, the object that's underneath is called the radicand. And the type of root that you're taking, which for us is a square root, we do not write the 2, that's implied. That is called the index, and we're going to go over that more in the next lesson. And this symbol right here is called a radical. So oftentimes when we see something like this, we say radical 2. Or sometimes people say the square root of 2. Oops. The square root of 2. And sometimes people just say, sometimes people say the principal square root of 2. And the principal square root of 2 is going to be the positive square root of 2. Which means the positive square root. Okay, so if we are going to simplify, so let's say that I have the square root of 12. Now, the simplification process is built on one simple rule. If I have the product of something, if I can break down the radicand as the product of 2 factors, I can put those factors under their own square root. Okay, and that works with a cube root, a fourth root. It works with a root, with any type of root. Anytime I have a product inside, I can break up the product into 2 simple ones. Also, anytime I have 2 roots that are the same type of root that are being multiplied, I can put them together under the same symbol, because maybe I want to do that. Maybe when I do that, I can get a perfect square root and then actually take the principal square root of that. Okay, so we'll look at that in just a second. Now so for this square root of 12, I'm going in this direction. Okay, so for the square root of 12, this is how you want to think of it. 12 has many factors, right? It's 1 and 12, 2 and 6, 3 and 4. And I could make them all negatives, but I don't really want to do that because I don't want to take the square root of a negative number. That would be an imaginary number, which you're going to deal with in Algebra 2. So I want to think of the factor breakdown that gives me the greatest possible perfect squares. So there's no perfect squares in the factors 1 and 12. There's no perfect squares in the factors 2 and 6, but there is a perfect square in the breakdown of 3 and 4. Now, I do that because when I break it down, so I'll break this down into 4 times the square root of 4 times 3. When I separate them into their own square roots, what happens is I can actually take the principal square root of 4. That's an integer. I mean, I can take the square root of any number. It would just be an irrational number. But I can, the square root of 4 is an integer, so that actually simplifies a little bit further into 2 times the square root of 3. Okay, meaning the square root of 4 becomes 2, and since I'm multiplying that by the square root of 3, 2 just becomes a coefficient. So this is a coefficient of the radical, much like you have a coefficient of a variable. Okay. Now, the one thing that I wanted to mention when we deal with radicals is that, of course, I can take the square root of a number. Okay, if I took the square root of this number, I would get a number that neither terminates or repeats, right? This is going to be an irrational number because anytime I take a root and it's not, so anytime I take a square root and the radicand's not a perfect square, I'm going to get an irrational number. So the number neither terminates or repeats. So I'd have to write, in order to write the number in its exact form as a decimal, I'd have to continue writing until I was, old, and then, I could never, what I'm trying to say is I could never get to the end of that number, right? Because it never terminates, it never repeats. I could write to the end of my life. My child could pick up that same task and write to the end of their life. Their child could pick up the same task, write to the end of their life, and I would never get to the last digit of the decimal representation of this number. Okay, so the most exact form of the square root of 2 is just this symbol right here. Okay, remember that's an idea that indicates that we're looking for the number that when multiplied by itself it gets 2. And it turns out when we do that, right here we get the it's not super long, it's infinitely long. Okay, it's longer than anything else we know of, okay? So when we deal with radicals, this right here is the only exact form of a radical, unless it's a perfect square. If any time you want to represent it as a decimal, you are doing some sort of approximation. Even now when I wrote this down, this is an approximation. Okay, the decimal representations of irrational numbers are always approximations. Okay, so that was just a side note. Let's go back to simplifying here. So if I simplify 50, I really, again, I want to think of the factors. If there's any factors that's a perfect square, and there is, 25 is a perfect square, I want to write that first and write the other factor next. And then I can break it up into these two radicals. And then 25 becomes 5 times the square root of 2. So I really have 5 of these square roots of 2. All right, it's important to think of that for the next step, which is going to be adding like radicals. Okay, let's say that we have a fraction here. Now, for this fraction, 3 is a prime factors, but 8 has factors of 2 and 4. Okay, so what I want to do is I want to break up the numerator here into 4 times 2 and the denominator into 3. Now the other rule, if you have a fraction, you can split the numerator and the denominator into their own radicals. So what I'm going to do is I'm actually going to rewrite this as 4 times 2/3. Okay, I'm actually not going to use this rule right now. There's many different ways to simplify this, but right now, instead of 4 being in the numerator, I'm going to bring that 4 down into as a number being multiplied by the fraction 2/3. And remember, I'm allowed to do that because if I multiplied 4 over 1 again by 2/3, I'd get what I had here. Okay, so here I can use the multiplication property of square roots, which is now I can multiply it like this, and what I really have is 2 times the square root of 3. Okay, I could have used this property right here by, let me just do a different way of simplifying. Again, there's many different ways to simplify. I could have put them under their own square roots like that. Then what I could have done on the top is break that down into 4 and the square root of 2, and I still have the square root of 3 on the bottom. And then this would become 2 times the square root of 2 over the square root of 3. But again, just like I can go in this direction, I can also go backwards. So if I have a numerator and denominator each under a square root, I can put them together. So this would arrive back in this location. Okay, and that's this second one's more simplified because there's less radicals in this one. Okay, now let's just go through this. Now the square root of 18, I want to rewrite that as the square root of 9 times, and right here I can just skip that step where I put them under the same square root. I can rewrite this as the square root of 9 times the square root of 2. And this would become 3 times the square root of 2. Okay, 4 times the square root of 150 becomes 4 times, now 150 has 25s in it. Let's see how many 25s. It should have 4 5s, so it's 6 times 25. So let's just do this right here. Okay, now 25 becomes 5. So what you're really doing is you're taking 4 and you're multiplying that by 5, because this is just the integer 5, and now everything's being multiplied. So you really just have 4 times 5 times the square root of 6, and that becomes 20 root 6. Okay, now we have another fraction here. So the numerator is a perfect square, so it's going to be helpful to me to do this. Okay, so this becomes 3 over radical 2. Now we don't want to keep the square root of 2. We don't want to keep a square root in the denominator. So what we often do, this is part of the rules that you'll learn in like pre-calculus. What you want to do is you want to take the square root out of the denominator, and here's the trick. Okay, the trick is to multiply the denominator by the square root of 2 over the square root of 2. Now I know that seems really strange, but remember the thing that's in red here is just equal to 1. So I'm allowed to multiply that by 1. The reason why we do that is this, it doesn't really make sense to you a lot now, but in pre-calculus you'll be able to see why this makes sense a little bit more. I'm sorry that you have to wait that long, but you're just going to have to trust me on this. Now, it's just sort of convention, is what I mean to say. So in the bottom here, the square root of 2 times the square root of 2 becomes the square root of 4. Okay, in the top we have 3 root 2. Well, the square root of 4 just becomes 2. So this fraction simplifies into square root of 3 times 2 over 2. Okay? I know that seems very strange, but that is the process that we go through when we have a square root in the denominator. It doesn't matter if we have a square root in the numerator. What we're really concerned with is not having any square roots in the denominator. And actually, I can go ahead and tell you one of the reasons that I've just remembered. You know, when we have a square root in the denominator, when we start to add when we start to add fractions with radicals in them, we want the denominators to be the same. So we don't want denominators that have square roots in them because it makes the adding and subtracting process of these fractions a little bit more complicated. So by convention, we just write the denominators as integers, but the numerators can be as complicated as we like. But the denominators, as long as they are integers, then we generally say that that's a simplified radical. Okay, now 4 times, this is the first time we've had a power of a variable here. So I'm going to break this down into the square root of 4 times the square root of y cubed. Now, y cubed has a square root in it. Okay, the factors of y cubed are y squared, which is a perfect square, times y. So actually, I'm going to break that down further into these two factors. Okay, so let's simplify square root of 4, which is 2. Now, I'm going to break this down as the square root of y squared times the square root of y. So, and this simplifies to just y. So what I have is 2 times y times the square root of y. And that is as far as I can go. There's no other perfect squares that I can pull out of that radical. Okay, so hopefully you've taken good notes here because this will help you when you do this process in class. So what we learned to do today was we talked about the vocabulary associated with radicals, the radical, the radicand, and the index, and we talked about how to simplify radicals by pulling out as many perfect squares as possible.